Okay, hello everybody. So today we're going to cover the last section out of Chapter Two's Section 7, and I'm going to talk a little bit more about what it means to be one-to-one. I touched on it briefly in the last video, but I'm going to go into a little bit more detail where we are going to discuss again how to test for one-to-one, and then we're going to show you how to use that as we're trying to find various inverse functions. So let's get started. First of all, the reflective property of the graphs of inverse functions gives you a nice geometric test for determining whether a function has an inverse function. This test is called the horizontal line test for inverse functions. And as I briefly spoke about in the last video, a very quick way for us to determine whether a function is one-to-one is to simply pass a horizontal line through it. We have had a previous test, probably back from Algebra 2, where you were taught about the vertical line test, which tests whether something is a function. Once you know that something is a function, you then can test it with the horizontal line test to see whether it's one-to-one. If a function is one-to-one, then it will only pass through a horizontal line one point. If it passes through more than one, then it's not one-to-one and it will not have a function. So it says, consider the function given by f of x equals x squared. The table on the left is a table of values for f of x equals x squared. The table on the right is the same table, but on the left, but with the values in the column interchanged. So the point that they're trying to show you is that, and what I showed you before with this graph, is when you have a function and you have its inverse, the ordered pairs are going to flip-flop. They're going to flip-flop. That's what happens. So if you have a function that you say, okay, yes, this is a function, there are no repeated x's anywhere. And if you look over here, none of the x's repeat. But if I would find the inverse of that function, what you end up seeing is all those x's became y's, but we had some repeated y's over here. But what ended up happening is all those y's now became x's, and we have repeated x's. That's a problem. We can't have repeated x's. If you have repeated x's, then this would not be a function. So we can't invert graphs that have repeated y's, because when we invert them, the y's become x's, and then it fails to even be a function. So we need a way to test for that, and that's where your horizontal line test comes in. It'll save you time of trying to find an inverse if an inverse doesn't exist in the first place. So it says applying the horizontal line test. So it says the graph of the function is given by f of x equals x cubed minus 1 is shown below. Determine whether the function is one-to-one. And so what you can see is no matter where I place a horizontal line, and that wasn't very straight, but you get the idea. It doesn't matter where I place horizontal lines in this graph. It will always only ever intersect the graph in one place. Therefore, this function f of x would have an inverse, and we would be able to find that inverse. Now, if we look at this graph, and this is a graph of a parabola again, so parabolas are an easy example, and that's what I showed you in the table, and that's even what I showed you in the previous video. A parabola would not pass the horizontal line test because it intersects in more than one place. And remember, once we find the inverse, the x's become y's and the y's become x's, and then once the y's become x's, we would have a repeated x, which then would fail to be a function. So this would not be a function. This would not be one-to-one, therefore would not have an inverse, unless you restricted the domain like we did in this problem from the previous video, where we restricted x to be greater than or equal to 0. Now, the next thing that I want to show you is how to find an inverse algebraically. The first couple videos when we talked about finding inverses, we only found those inverses intuitively. So if we had a function that multiplied all the inputs by 4, then our inverse function would divide all the inputs by 4. So that was kind of easy to understand. We're just doing the opposite operation. But what happens whenever we get into super complicated equations? And this is not even a super complicated complicated one, but they do get more complicated, or even multi-step ones. How do you know what to undo first? Well, there's a very simple way to go about finding an inverse algebraically, and these lay out the steps of how to do so. It says use the first thing you want to do is use the horizontal line test to determine whether the function that you're working with even has an inverse. You don't want to spend time trying to find an inverse if it doesn't exist because it doesn't pass the horizontal line test. Now, once you verify that it passes the horizontal line test, you want to go ahead and replace the f of x with a y. So you're going to take it out of function notation and just make it y equals. And then you're going to interchange the x and the y variables. So where there's a y, you're going to write an x, and then where there's an x, you're going to write a y. Once you do that, you are going to then resolve for x, and the new function that you get will be the inverse. So let me show you how this works. So we're going to find the inverse function of this. The first thing I'm going to do is I'm going to rewrite this so it's simply y equals 2x minus 4. So there's really no change there other than to get rid of the function notation. Now I'm going to go ahead and interchange the two variables. So I have x equals 2y minus 4. And now that I've switched the x and the y, I need to resolve for that y variable. So I'm going to add 4 to both sides. So I get x plus 4 equals 2y. And then I'm going to divide both sides by 2. And I'm going to get y equals x plus 4 over 2. And the last thing to do is replace that y with an inverse. So we're going to call that f inverse of x is equal to x plus 4 over 2. And there you go. That's the inverse. So this function and this function are inverses of one another. If I wanted to verify my work was correct, I could compose them together. And if I compose them together, I should get the identity, which I will. All right, so here's another one that we're going to take a look at. So you can see this one's pretty complex. I mean, there's a lot going on to that variable x. It's being multiplied by -3, and then there's a adding, and it's being added to 5, then it's being divided by 2. So that's a lot to try to undo in your head. So we definitely need the algebraic way of finding the inverse. So same thing, we're going to start by checking to make sure that this thing actually is 1-to-1. So there's the graph of this. You can see it would pass the horizontal line test. So the next thing we're going to do is and that's not the right graph. I apologize. The graph of this would be a linear, it would be a linear graph. And I can show you on my graphing calculator here. Sorry, I had changed that problem and I forgot to change the graph. So this would be 5 minus 3x divided by 2. So if we look at the graph of this, you're going to see it's just a line, and that line will pass the horizontal line test. So this function will have an inverse. So let's go ahead and find it. First thing to do, we're going to drop the function notation. Then I'm going to switch the x and y's. And then I'm going to go ahead and solve for y again by multiplying both sides by 2. So I'm going to get 2x is equal to 5 minus 3y. Subtract 5. So I get 2x minus 5 is equal to -3y. And then I'm going to divide by -3. And I'm going to get y equals 2x minus 5 over -3. And then if I write it in function notation, I just write f inverse of x equals 2x minus 5 over -3. And there you go. That's what we have as our function. So this function and this function are inverses of one another. Now, the last one we're going to take a look at is this one. It says find the inverse of f of x equals x squared. And I've already used this example a lot, so hopefully you realize that the graph of this would be a parabola. And a parabola does not pass the horizontal line test. It fails the horizontal line test. And because there's nothing restricted on there, you would just simply say the inverse does not exist. And that's it, because you can't find the inverse there. So it's always important to check your graphs whether they pass the horizontal line test before you try to find the inverse so you don't waste your time. Okay, so here's another one. We want to find the inverse of the square root of 2x minus 3. Now, 2x minus 3, if I were to graph that, it's the square root, and then we're going to put a 2x minus 3 right there. And go ahead and we'll hit graph and we'll take a look. You can see that that does pass the horizontal line test, so that is going to have an inverse. So we're going to go ahead, write y equals the square root of 2x minus 3. I am going to switch the x and the y's, so we have 2y minus 3. Now, in order to get rid of that square root, you're going to need to square both sides. So when I do that, I end up with x squared is 2y minus 3. I'm going to add 3 to both sides. So I get x squared plus 3 equals 2y. And then the last step, I'm going to divide both sides by 2, and I'm going to get y equals x squared plus 3 over 2. And if I rewrite this function as f inverse of x equals x squared plus 3 all over 2. So there's my inverse function. Now, I'm not sure if anybody sees a problem with that, but I'm going to go ahead and graph this and show you where the problem arises. So the function, I already have the first one in there. So if I do graph this second one, what we should see is a reflection of that graph about the line y equals x. But when I put x squared plus 3 over 2 in, x squared plus 3 divided by 2, and I'm going to graph that, and watch what happens when I graph it. So there's the line that it should be reflected about. I just put that in there so you can see. But here's the second equation. That is definitely not a direct reflection of the blue graph. There's too much going on there. And the reason why there's too much going on there is this is a full parabola. And this parabola is not a direct reflection. So what you have to understand is that we will never be able to work with x squared directly unless there is a domain restriction. So what we need to see is right here, you can see if we flip this blue line up, it would line up with the right-hand side of this parabola pretty well, but it would not have anything to do with the left-hand side of this parabola. So we would need to split this parabola down and completely eliminate the left-hand side of that. So in order to do that, we need to put a restriction in. And what we want to restrict is we only want the x values of that parabola that are greater than or equal to 0. So I can go ahead and go into this. And if you recall, I did show you guys how to do domain restrictions back whenever we talked about piecewise defined functions. But you're going to hit divided by, and then you're going to do the restriction. And you have to go to test. We want x's that are greater than or equal to 0, just like that. Now, once I hit graph, you're going to see now there's the blue one. There's the line that the graph should be reflected about. And then here is the black one, but we only have the right-hand side of the black one. And now those two are reflections of one another. So going back to our notes here, then, we would need to say that x has to be greater than or equal to 0, since we are dealing with a full parabola and we only want half of it. All right, guys, that's what I have for you today. I hope that made sense. As always, if you have any questions, feel free to email me. Have a great day.